All right, let's get started. So today we're going to talk a little bit more about the Flash Array product line and what's going on there. Did the morning with the Flash Blade. So let's see if we move forward. So what we're going to talk about is we built quite a bit of capabilities. We built a platform, and our vision is basically trying to put data to work end to end. We trying to make it effortless, scalable, try to make sure it works across all the protocols, files and objects, and then block protocols. And Purity is really the fundamental underpinnings behind all of it. And we spent, for this year, we spent quite a bit of work adding a lot of capabilities to that. So what we're going to announce, and this is the overview, we're going to announce basically 25 new software features. And we're going to talk a lot about getting really deep into the tier 1 type of workloads. Speak a little bit about sort of big data and big intelligence. That's largely on the FlashBlade side. And then we'll speak a little bit about sort of self-driving storage and what we're doing with the Pure 1 and the Call Home stuff. And I think you'll find it interesting. So if I set that up and using the really pretty marketing slide that I'm going to show tomorrow, the new tier 1 is what we're trying to redefine, and we try to change our product to make it sort of really suitable for that and pushing the boundaries on what that classical has been. Historically, I think this has kind of been the narrative set up around tier 1. It's kind of built for the cloud era, but you can't go there because you got to have the reliability. And it's kind of been positioned as these two very conflicting priorities. And what we're trying to do is unify those, build really massive reliability. I mean, today we're at about 6 nines of reliability, availability, demonstrated through our fleet in the field, as well as build things that are aimed for a cloud, that's ready for the cloud. And if you kind of put that together and sort of, here's the things that we're working on. So uptime, always, availability, resiliency, and we measure that daily. We get daily reports basically from our support side on our fleet uptime. We're introducing ActiveCluster, and that's what we're going to talk about today. We're introducing quality of service and vWalls. I'm going to spend a little bit of time talking about the cloud integration and kind of how we work with the cloud and not against the cloud. I'm going to spend a little bit of time talking about efficiency, NVMe, and finally Evergreen. So let's get started. Today, you'll hear from experts in the field. You'll hear from Tabriz and Larry about ActiveCluster, NVMe, Pete and Angad, and vWalls, Cody. And let me get out of the way and get these folks on stage and get started. Thank you, everyone.
Hi, everybody. My name is Tabriz Holtz, and I'm an engineer on the ActiveCluster team at Pure Storage. Also today with me here is Larry. We're going to kind of have both of us mic'd up so we can kind of have a conversation about our ActiveCluster product. So about 2 years ago, we kind of entered into the synchronous replication, thinking about entering into the synchronous replication market. At that time, we kind of thought about a lot about how do we want to come out with a synchronous replication product. There's obviously coming out with like a minimal viable product, which is what a lot of companies have done. But we really took a step back and started thinking to ourselves, let's really go out and really look at the pain points that our customers have and see if we can address them like full face, right up front with the first version of our synchronous replication solution. So some of the things that we kind of learn when talking with customers is there's kind of 5 main points that customers want in a synchronous replication solution. They obviously want disaster protection. That's the reason that you purchase a synchronous replication solution. So in the event of a disaster like a flood, earthquake, power outage, evil monster, you lose access to some of your data on a particular site, you have another piece of that data at another location. But that's really just not really all that customers want in this type of solution. They want consistent performance. They want transparent failover, the ability for their applications and their data to be online transparently during a failover without manual intervention in as much as possible. Ease of management is key. I've heard some of these solutions can take days or weeks to deploy, and some even require a service contract for a physical person for many days to set up. But I think one of the things that kind of goes throughout all of our product line is a subscription to innovation. And that's the idea that there may be some pain points that we know today, and we may be able to address that with a product. But those pain points are ever changing. The market is ever changing. And so customers don't want to have to wait until their next refresh cycle in order to have those pain points addressed. So with our with a purchase of a flash array, customers automatically get a subscription to innovation through the Purity upgrades that happen. And that it will be true as well with our synchronous replication solution. So what they really don't want is they don't want to pay a whole heck of a lot more for this. You're already purchasing multiple arrays to get your disaster protection. And on top of that, you don't want to have to pay licenses. Some companies, I think, require licenses purchased on both sides of, on each of the arrays that are purchased. And you don't want to have to pay for additional hardware in addition to those two arrays. But I think most importantly is that people just don't want their life to suck because they decided to protect their data. As much as possible, applications should be unaware whether they are sitting on top of a single pure storage array or on top of a disaster recovery solution. So at Accelerate, we are announcing our Purity Flash Array ActiveCluster. It is our synchronous replication solution. And it has these main features. It is an active solution where you can read, write, and modify to both sides of the cluster. It has a 0 RPO, a 0 RTO. It costs $0 additional on top of the purchase of the arrays. No licensing, 0 additional hardware, transparent failover, transparent recovery, and through all of that, we really tried to put a lot of effort to maintain simplicity and maintain consistent performance. So let's look at the basic architecture of ActiveCluster. It's comprised of 3 main components. Starting in the middle here, you have your 2 flash arrays at different physical locations. They provide a symmetric active-active access to your data, so you can read and write on both sides. And here on the bottom, what we have is a representation of our data management model. Yes?
Are you saying active-active, you can write to a volume at the same time?
You can write to the volume at the same time, on both sides at the volume level, right? So in some sorry?
The volume, you're talking about a LUN can be written from the same LUN can be written from both sides?
Yes.
Is it like a multi-master situation?
But the cluster file system's responsible for integrity.
Yeah.
I'm sorry?
Is it like a multi-master, like my write goes here and then it gets acknowledged to the other source and then back?
So we'll talk about the data flow in a little bit, but it is, there is control in there to ensure that you have your write ordering, that writes never get acknowledged on different orders, they never get exposed in different orders on each of the different sites. But yes, down to the LUN level, you can actually write data on both sides, as opposed to other solutions where you have volumes writable on both sides, but they're actually active passive underneath the covers. So the Podman.
Do you find there's a lot of need to have a volume be written at 2 different sites at the same time? I mean, it doesn't seem like it's a big customer requirement, but I don't know.
Certainly, it doesn't. There are a set of customers that may not be interested in this, and that is certainly part of it. But when you start talking about, oh, sorry, the question is, do we find many uses for or interest in situations where they want to be able to write both sides on both sides of the array?
Motion is really a writer at one point, just moved from one place to another.
But from the array that only knows about, but that's VMFS managing it, not the array.
Yeah, so you'll see when we do, so I'm going to follow Tabriz up in a few minutes and do a live demo. So the reason we need the LUN to be writable on both sides is it gives us a lot of flexibility about where you run your workloads, where you can run your virtual machines. But it's by far, the same LUN being active on both sides is by far the
same volume at the same time from 2 different locations.
You have to have clustering. You have to have cluster aware hosts doing it, right? So they're not separate. Yeah.
Yeah, I mean.
But does it have to be that? Can you make it active passive?
So let's if you don't mind, if we'll go down a little bit further, and we'll see kind of how some of this is set up, because I will go into more detail into these things, and so please re-ask your question if I don't address it. And so our pod, this is our new management model. It's called a pod. It is simply a container where you can store your volumes and your representation of the replication policy that you desire. We'll dive more into that as well. And then in addition, we have a mediator. The sole purpose of the mediator is to prevent split brain should the two arrays no longer be able to talk to each other.
That's a cloud mediator?
Sorry?
It's a cloud mediator?
So
implying it's in the cloud, or can you have something on-premise also?
Yeah, so we'll talk about why we have the option of a cloud mediator in a couple of slides. But yes, we do have a cloud mediator option. We also have an on-prem VM option. Make sure you talk. Okay, so starting with pods. Pods, really here I put the Webster Dictionary definition here, modified only slightly. But the interesting pieces here is that when we talk about a pod, we're really talking about a container, a detachable, self-contained container that serves a particular purpose. Okay, and in this case, the purpose is to describe a replication policy. And for example, let's assume that we have a pod here with a volume V1. When you take a snapshot of that volume V1, it automatically inherits the replication policies associated with the pod that it resides. So you don't ever have to think about things like, I have a volume that has this replication policy, I take a snapshot, now what do I do with the snapshot? Is that automatically replicated? Question, 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 right? So you automatically get that by deploying inside of a pod. Same thing with taking the snapshot and cloning it to a new volume, right? In addition, you get statistics per pod, so you're able to accumulate per pod and view them that way. So this is the kind of high level of pod, and what I kind of wanted to show in is just how simple pods make the setup of this solution.
Didn't you say at the beginning that this was multi-site?
Multi-site, yes.
Yeah, so does that mean you can have relationships going in different directions?
I'm sorry, relationships?
Does that mean you can have relationships between different machines, different arrays in different directions?
Yes, okay, yeah, that was a good question. Yeah, I'm sorry. I kind of glossed over something here. When I'm showing the pod here, I'm showing it as it's stretched across multiple arrays. And one aspect I didn't really say, which is the really important aspect of this definition, is a pod is a detachable unit, meaning it's not necessarily hardbound to any particular array. You can stretch it across multiple arrays, and then you can detach it from some set of those arrays. And what that implies is that later on, what we can do is we can actually dynamically move this pod throughout the cluster. So it is totally true, although we're in beta and the demo is not going to show this, it is totally true that down the line, what we fully envision is supporting things like a pod stretched amongst array 1, array 2, and array 2 and A3, right? Very flexible. So I talked a little bit about simplicity and how important simplicity is at Pure Storage. That's just a general philosophy that we...
Replication between three separate arrays? It's really two sets of replication between three arrays.
Well, okay, so there's nothing precluding us from going into replicating to 3 separate arrays. In our first version of the product, we are only going to have a pod stretch amongst 2 arrays. What I was really referring to there was the latter of what you said, was 2 separate pods stretched differently amongst 3 different arrays. So one of my favorite beta customer stories was that the customer in our beta program actually went to go set up his ActiveCluster setup, ended up calling his SE and saying, hey, don't even bother coming over here. I already got this thing set up myself. And the real reason is we kind of painstakingly took steps to make sure that the setup of the array and the setup of the ActiveCluster followed our simplicity model. So the only command that we actually add in order to set up an ActiveCluster is in step 2 right here, where we create the pod and then we add the array to the pod. So we were able to do things quite simply. So let's talk now a little bit more about the guts of the active-active solution. This is my favorite part of the system. I'm probably slightly biased because this is the piece I worked on. But when I think one of the questions is why did we do active-active? I mean, there's a lot of active-passive solutions out there. It fills a lot of set of the market. Why do we go active-active? I think one of the reasons was if I came up here and presented an active-passive solution, I would assume that probably a logical next question would be, when are you going to implement active-active? So we were kind of trying to think ahead of the game a little bit and thinking like where, kind of think about what solutions are going to be wanted down the line. Well, the second thing, which I think is really the reason that we ended up going with the active-active solution, is that we recognize that going from an active-active to an active-passive solution is far more straightforward than going from an active-passive to an active-active solution. So we really decided to bite the bullet out of the gates and go with an active-active solution, and then believe that we'll be able to deploy an active-passive solution or a prod DR solution down the line faster. So when we talk active-active, what do we mean? Well, what we really mean is that we support both reads and writes on both sides of the array. For the reads, we're actually only servicing it on one site. It doesn't take a round trip across the network. So if you're deploying an application on top of a single flash array versus a symmetric an active cluster, you shouldn't see any distinguishable performance differences. Writes or modifications, on the other hand, can come into either side, but then are replicated across between the two arrays. And the symmetric part of it, which we really like to highlight here, is that we wanted to ensure, there was a comment about, is this I forget what it was, a multi-master or something like that comment. We really want to ensure that customers never know underneath the covers who's what, right? To them, you've got two arrays, and you should be able to operate on them either way. You should not be able to distinguish the performance between writing to one array and writing to the other array. So the way that we do that is we ensure that you take at most one round trip between the arrays, regardless of which host you come in and which array you talk from. Now, that's on the array side of things. But we also need to ensure, if you have a connection, a uniform connection as shown in this picture above, we also need to ensure that you're not taking other round trips between the host and the array. In order to do that, we implement ALUA preferences. ALUA allows you to specify which paths are considered optimized and which paths are considered non-optimized. In this case, orange is represented as active optimized, and blue or green is represented as active non-optimized. So it is also, I should say, a host-based ALUA preference. So should you have an application that migrates from one site to another site, it automatically will start talking to the host. That's the array that's closest to it.
Okay, so in that scenario you showed on the previous slide, if either side can write and you've got an application that's behaving well, that's all fine. But if you've got an application that doesn't behave well and you get two writes that come in for the same data at the same time, how do you decide and arbitrate which one is treated as the one that is accepted and rejected? Okay. And obviously, there's a timestamp that's going to be there that says one arrived before the other, because I think it's unlikely they're going to arrive at exactly the same time. But somehow you've got to reject the one that comes in afterwards if the other one's already been written.
So we don't reject, but you're right, and I'm not going to lie to you that there's not a concept of a leader and a follow underneath the covers. Okay, one of these two arrays will determine the order in which the writes may be visible on the storage. And that ordering must be guaranteed to be the same on both sides of the array. So, that's it. We don't air out those IOs. We just ensure that the ordering is maintained. Whenever we forward an IO from one array to another one, we say, hey, you have a second write that came in. It is predicated on the fact that the first write exists before you're able to execute this write.
Going back to that again.
Okay.
If I write on the left array, and the I.O. doesn't happen instantly. It takes a finite amount of time, during which an I.O. comes in the other side, and you acknowledge to the primary one. You acknowledge to the primary before, or are you rejecting the I.O. when it comes across to the second side because you've seen a write come in for that same data, and therefore it can't be acknowledged. You effectively reject it.
You have to have you have to have a cluster where application sitting on top of this, right? So the application is going to manage where it's doing its writes, right? So if it's
I get that.
yeah, I don't know. Then it's going to. I mean, if the application misbehaves, then that's an application bug, right? I mean, like applications are supposed to issue dependent writes, right? So if it's a SQL cluster has an instance of a database that's live only on one node at a time. If the SQL cluster is allowed to go split brain and bring the same instance up active on 2 nodes at one time, like that's a bug at the application layer. Like we're not going to allow in ActiveCluster, we're not going to allow the arrays to both service data if they're not in sync. So from the application, from the host perspective, it looks like one copy of a LUN. So it only sees the same LUN serial number, the same LUN ID, and it's not going to issue non-dependent writes unless you've got some kind of bug in your app.
And if I do have a bug in my app, it's last writer wins.
Yeah, it would be last writer wins, yeah.
As far as the storage array is concerned, those 2 writes that you're describing, they're different writes. Yep. So it will write both of them. It will commit the second write because, yep, that's a new write. It's totally new and different, and it will overwrite the old one. And it's like, if that's not what you intend to do, yeah, do that.
But to Larry's point, that becomes an application level problem because the application
Correct.
Should be aware that we have this type of thing happening.
That's
Which
right.
brings, I haven't seen it on the slides yet.
Oh, no,
do we have
real-time
file system RTT requirements?
As if it was one array.
What are the requirements we have for the infrastructure in order to support this? Latency requirements.
So what we say is that we limit your distance to a 5 millisecond round trip time. When you want to talk about the additional cost of a write, we've got the cost of a local write, right? Plus the round trip time, plus a little overhead to do the ordering that you were talking about. So to ensure that we have that. So that's what we're looking like in performance.
What is the cross-array transport?
We use TCP/IP. Ethernet. It's IP-based networking.
Is the data that goes across between the 2, is it compressed and deduped?
It's compressed. We dedupe independently on both sides currently, but if you are doing a resync transfer, you'll get the benefits of dedupe that we get from our asynchronous replication engine. And I'll talk about how we get back into resync a little bit.
To clarify on the IP networking, is it what layer? Is it layer 3 or layer 2?
I'm not certain. Steve, where is Steve?
What was the question?
What layer of networking is it?
Oh. No, you can route it. Yeah. So we don't have any restrictions on whether it's routed or not routed. So as long as the replication ports on either array can access each other, it could be routed. I mean, obviously we want the best connection we can get. I mean, that's what we're going to recommend to customers, but they just have to be able to access each other.
Networking between the 2 is Ethernet?
VMware can't do it properly.
Yeah, the interconnect is Ethernet, multiple 10 gig ports per array, but between the 2 arrays.
Before we kind of go into the details of why we built it the way we did, I think it's most useful to look at an example. So before this X kind of appears on the screen here, our 2 arrays are talking happily. Once the 2 arrays detect that they are no longer able to communicate, they send a request up into the mediator. The mediator is a very, very simple stateless, okay, you hear me, okay? Stateless, a stateless VM, and the whole purpose of it is to decide a winner, okay? And it does that by doing kind of a compare and swap type instruction. And one side's going to win and the other side is going to lose. And when that happens, the contract is that the array that wins on this side, the left side of the screen, he's able to bring the pod, keep the pod online. Data access is uninterrupted. On the other side, we take the array down, because, not the array down, I'm sorry, the volumes in that pod down, so they won't be accessible anymore, and that's in order to prevent any kind of split brain. Now, the key things to kind of notice here is all the intelligence of the quorum is in between these 2 arrays. They don't ever reach out to the media. The meter never reaches back to it unless in an event of the lack of communication between these 2. And what this allowed us to do was to say, this is such a lightweight piece of software. What if we could provide customers a third site location, third fault domain in our Pure One cloud? And that allows people to deploy their Mediator in a totally third physical location. A lot of people who have a synchronous replication solution may not have that third physical location. And so this is a service that we think a lot of people are going to like. Now, if customers don't want that or you're a dark site, we have a VM that can be used as a Mediator as well.
So, quick question: is the Mediator a single VM or single instance, or is it a multi-master model? And any multicast requirements? Just wanted to cover those two.
So the VM is actually. Oh, are you asking?
Yeah. So the am I on? Yeah. So the cloud Mediator is runs multiple instances, and there's a load balancer. The on-premises Mediator that you can deploy is a simple OVA that you download and deploy, and it does the job of the Mediator. But you would have to, the on-premises Mediator, you would have to protect it with like VMware HA or something in your environment if you're going to use that one.
Sure.
Yeah. What if that happens and for some reason the thing that's causing my outage is a network failure and I've lost comms to the outside world as well as my remote site?
So So nothing happens in that situation because if you're Razor talking, they're going to continue going forward.
What I mean is, no, the problem I've had is some sort of issue with my network provider, which is actually affecting my cross-site communications, both my sites and external sites.
Okay.
So basically each of the Pures get isolated from each other and from the media.
Sure. So there's a three-way, there's nobody's able to talk. Right? So in that case, we take the stance that we're never going to allow a split plane to happen. And so what you do then is you take your volumes offline.
Yeah. So we do want to have independent access for the Mediator, right? So the infrastructure that you have shouldn't allow like one provider to shut down the connection between the two arrays and the connection from each array to the Mediator. And if you can't get that kind of a service from your provider, then you'd want to use the on-prem Mediator and put it somewhere where that's not going to be able to happen.
Could I do both? Can I have a cloud Mediator and a local VM Mediator?
They cannot. You can use both because it's actually a per pod setting that we'll have, but you can't use two different Mediators for one pod because they have to both talk to the same.
So I know what you're saying, in that you shouldn't do this and your provider should provide something which won't allow that to happen. That's what they'll tell me, and then they'll screw it up and do it wrong.
Yes.
And
anything that starts with should.
Yeah. Someone will make a mistake, and it will end up happening. And it's just, okay, when this happens, because it will, what is the impact for that? So I need to understand what that will be.
Yeah. Yeah, we're in beta today, and we're considering things like preferences and sites that will stay up, regardless of Mediator access and that kind of thing. But where we're at right now in the design and in the beta is that you need to treat access to the Mediator as a tier 1 service. So I do hate to use the word should there, but that's
okay. Okay, I've been told to move along here. So, sorry. So at the last slide, we were kind of in an out of sync scenario, and I kind of want to show what would happen to get your data back in sync. So we actually build on top of our async replication engine. So what that means is that we take a snapshot, we transfer that snapshot over to the other side, and continually do this in a loop until we determine that we're close enough in time that our last replicated snapshot took close enough amount of time that we're now going to start going into sync. And what that means is that we'll take a final snapshot, we will enable synchronous replication. At that point in time, you will be doing both asynchronous and synchronous replication. On this other side, we know how to stitch those two trees together, and once that final snapshot is transferred, you are now fully in sync. And the key point here is that we did all of this without any interruption, no I/O pause. So operations are happening through this entire cycle.